we are able to measure it more accurately and with less mechanical restriction. So you can make this leap to 80 dB SNR, 146 dB ALP, which is a 20 dB increase in dynamic range.
Hey everybody, Dave Lindbergh in Hong Kong with a new episode of THD Podcast. Thanks for tuning in. Please like, subscribe, all that good stuff. And today we have Sensibel, a company headquartered in Norway, Oslo, and they're doing something different. Instead of the traditional capacitive MEMS microphones, they're doing some kind of laser pickup and able to push the sensitivity level through the roof. And it's some amazing data results. So we're going to find out how that works. But without delay, shout out to our sponsor, the Alti Association. They're going to be at Expona coming up in Chicago in April and High End Vienna in May or June, whenever that is. So please encourage people to go check that out. And also the Audio Express. There's probably some good coverage of Sensibel that you could read about. If you're interested in what we're talking about today, you can go there and look for more information. So without delay, let's say hello to everybody. So we've got Simon in Sendai, Japan. Good evening, Simon.
Good evening.
All right, and Michael Tuttle, the applications lead for Sensibel, and we've got Tom Hazlett, the VP Global Sales. Thanks, guys.
Yeah, absolutely. Thanks for having us.
Yeah, I've been tracking you guys
Likewise.
for a little while now, but it seems like you guys are ready for prime time. So yeah, let's tell people what you guys are up to. It sounds exciting.
Well, again, thanks for having us, Dave. Simon, nice to meet you. Mike, go ahead and go to the first slide if you don't mind. And we'll notice
Sure.
we won't talk too much about the awards. You saw down there we have a couple awards. It's been a good year thus far. So we're spending a lot of effort on branding, and I'm hoping between LinkedIn and such, you're going to start, if you haven't already, you're going to start seeing a really big increase in branding and opportunities and companies we're working with. So it's all going to be very positive this year. So very excited for that. So as Dave said, we are a optical MEMS company based out of Oslo, Norway. You'll kind of understand a little bit maybe how it came about that we're in that region. We'll talk briefly about Syntef, but the core technology we have is over 10 years of research, and you'll see the name Syntef. It's a research organization, probably the largest organization in Scandinavia, and all this technology ultimately has evolved from the research that Syntef has been doing. They research MEMS, optics, and acoustics. We've been fortunate to benefit from all of that. Currently, we're probably just over 30 employees. I think that's pretty accurate. Mostly in Oslo. Mike's in Ireland. I'm a Floridian, and then we have a couple people in Boston. Our CEO, our COO are in Boston. But generally, everyone else is in the Oslo, actually kind of spread out in Europe, but mostly in the Oslo area. It takes investing. We're fortunate to have some pretty well-known investors. You'll see AAC's name quite often. They're an investor, but they're also our back end. Obviously a very big name in MEMS mics. One probably in the top three if I had to guess, but they do all of our assembly and test. Sennheiser, European, very well known as an investor, and we're hoping soon a customer. And then IQT, which is kind of a new organization for me, but they're here in the States and the US, and really do a lot with technologies, very government oriented. So, this was I'm relatively new with Sensibel, officially the beginning of this year. I was kind of thrown in the fire. I think I started on the 5th of January. On the 6th, I was at CES, thrown right into the fire. So it was a very good event for us, lots of interest. But so the history of Sensibel, it's again fairly new to me. But in 2010, here's at Syntef that I had referred to. They are a research, probably the largest research organization in Scandinavia. Innovative research, technology, and that's ultimately where we started. A little incubator, I guess you could say. In 2010, our first prototype. And then in 2017 was when Sensibel was established. So we've been around for a number of years, and I'll talk a bit about that. In 2022, we had our first SBM 100 samples. So this actually proved the capability of the 80 dB SNR, and again, that's really the key feature and the key buzz. Certainly everyone that was coming to CES and coming in the room saying, "Is this real? Is this real?" Well, and in 2022, we confirmed, verified that it could be real, and it is real. So that's when we started in 22, probably 22, 23. We engaged with customers. And then Tony Minervini, I'll just throw a shout out to him. Tony Minervini, I worked with him at Knowles many years ago. He was with Apple for a long time, really a leader in MEMS packaging. The guy just is phenomenal. And when he came on board with Sensibel, probably around 23, I think, 2022, 23. He changed the design, and now it really is mass producible. And as of 2024, with our first SPM 100 really production worthy samples, that's what we're shipping today right now, and it's largely very well. I can't say it's due to everybody, but Tony really had a big part of it, and we really have a fantastic product that everyone is evaluating today. So here we're supporting hundreds. Well, we've supported well over 100 customers with the current product, and things are looking quite fantastic right now.
Quick question, this concept of optical MEMS, is there optical MEMS microphones? Is there other optical MEMS devices?
I think there are some optical gyroscopes. I don't know that much about them, but I know for high precision, people have made optical detection gyroscopes, but I don't think it's been it isn't that common.
Not miniaturized. Mostly any research I've done, it's all been fiber optic, some form of a fiber optic acoustic transmission, vibration type sensing, but it's all been fiber, not miniaturized like we've done.
Okay.
And
yeah, and
you're gonna get to it though, but is it like just to try to understand it? It's a reflective, and it's picking up the reflection. You're going to go into this in a bit for us.
Yeah.
Okay. Well,
yeah, absolutely.
Stealing our thunder, Dave.
Okay. Sorry.
Yeah, and that's something that we've a good drawing that will illustrate how it works.
Okay.
But I guess just to look at the big picture and comparing audio capture to video quality. If you look at the evolution of smartphones, the first smartphones had some reasonable cameras, but they improved dramatically. And now you have, smartphones with 8K, multi-lenses, and all the types of advanced imaging there are out there. And it's all in your latest iPhone. But the audio has had more incremental improvements. So it's maybe gone from, just 60 dB SNR or below to adding a few more microphones, but not driving the performance to the same kind of levels that the cameras have seen. And maybe on the latest iPhones, you're starting to see some audio features like the spatial audio mix that's enabled by microphones up around 70 dB SNR. And we really feel that 80 dB SNR is a very disruptive technology and will enable the audio to catch up to the video. And that's not just for smartphones. You can apply this over a number of applications that we'll talk about later.
Okay.
So yeah, so our optical MEMS microphone, an exploded view is shown on the left. There's a few more components to it compared to a regular MEMS microphone. In addition to having a MEMS and an ASIC, we have an optical module that's built around the MEMS where you shine a laser, put it through a diffraction grating, and then have a photo detector that picks it up. And this technology allows us to have huge leaps in performance with 80 dB SNR, 132 dB dynamic range, and 146 dB acoustic overload point.
Hmm.
So
What
let
was
me
the point about
clarify too. So the idea is that there is no charge backplate. So in a traditional ECM, whether or not you're talking a very traditional old school ECM with a 200 or 400 volt film, charged film, or a more traditional capacitive MEMS, which with a 10 volt backplate, we don't have a backplate any longer. So, and that's really where a lot of the noise in the system comes from. And so we've been able to eliminate that backplate, and now the measurement, and again, you think about that, that is a capacitive measurement system in a traditional MEMS. What we've done is we've just completely removed the backplate, and now we have an optical measurement system.
Okay.
So curious. So there's we talk about SNR and 80 dB SNR, but it's just another way of saying what's the equivalent SPL lower limit, right? Which is actually a more meaningful number if you ask me, because I'm pretty sure 14 dB is pretty well below anybody's hearing range, isn't it?
Yeah,
Quite
I think some of the
significantly.
close. What's the closest, Mike? 20? I think might be the closest that I've
Yeah,
seen.
the leading MEMS microphones right now are would be 22 dB EIN, and most of them would be in the high 20s. That would equate to just about 65 to 70 dB SNR. So there's a lot of benefits to such a low noise floor, and we'll go on to talk about them. But and actually on the next slide you can actually see the level of performance improvement. So on the x-axis here, we have the acoustic overload point, and the y-axis is the SNR. You could equally have it as, like you said, Simon, the input referred noise, and have it as a decreasing number as you go up. And effectively, if you look at the leading capacitive MEMS microphones available today, and they have different combinations of SNR and AOP, and they can gain a bit on SNR if they trade off some AOP, and vice versa.
Yeah.
And they end up like having little skews where they can have a specialist mic for different applications. But fundamentally, they're in this trade-off space, and we believe they can't break out of this frontier easily because of the capacitive technology and the squeeze film damping between the plates. We have a more simple MEMS, and we are able to measure it more accurately and with less mechanical restriction. So you can make this leap to 80 dB SNR, 146 dB ALP, which is a 20 dB increase in dynamic range. So this is a generational leap enabled by the optical technology, and it's a really, really disruptive.
Yeah, it's very much a step change in physics, I guess, isn't it?
That's
Absolutely.
right. And these are the fundamentals that enable that. With the capacitive MEMS microphone, you have a membrane and a backplate and a small distance between them, maybe like 2 microns. With the Sensibel optical MEMS microphone, I talked about an optical module that's behind the MEMS. But ultimately, the MEMS itself is very simple. It's just the membrane. It's like a drum head. So you don't have that backplate for it to touch against or to be a source of noise. So this allows you to have very high SNR. We've no backplate, significantly lower noise. Whereas on the capacitive mic, that's a major source of noise. The overload point, the increased overload point comes from the ability of the membrane to move more. So on the capacitive MEMS, you have that 2 micron limitation. We're more than 20 times higher than that. So our membrane can move unrestricted and reach that 146 dB dynamic range. And then because we don't have this narrow gap, there isn't a possibility of the two plates sticking together through contaminants or electrostatic capture.
Okay. Yeah,
Really is a huge degree of freedom.
I was going to ask about dust and dirt, but I guess you covered that. And is it a special membrane material? Has the research gone into that membrane material to figure out how to get the range of motion and then also the laser pickup from it?
It's not too different a MEMS process, and the membrane has to be reflective to reflect the light back to the photodetector. So I think in the early years, a lot of development went into that, and now it's it's a pretty straightforward MEMS process and execution.
And is it equally durable? Like any alignment issues if you drop it? I'm sure this has been part of bringing it up to production ready, but I can imagine a lot of durability testing and refinement, getting this package together and alignment and everything to make it work as a unit.
Alignment, I think alignment's the key thing for sure. That's been, in our ramping of our current product, that's certainly been part of the issue. And that's as we move forward into more wafer level stuff, I think it might actually get a little easier, but we'll see.
Okay.
Yeah, I think in general, it's definitely from, it took more research to get all these issues figured out. But with the precision of assembly now, you can make things, manufacture them at scale very accurately and enable this type of miniaturization.
Okay.
What's the light source?
Oh, sorry, go ahead, Simon.
Well, what's the light source?
It's a VCSEL, so it's a vertical cavity laser. So it's it's a pretty standard, I guess, in the specialized industry type of laser. And we don't really talk a lot about what our exact combination of laser is, but it's a pretty common. There's nothing too crazy specialized about the type of laser.
You mentioned a little bit before about a diffraction grating. What is that? Where does that fit into it?
That's right. So that's part of the optical module, and it's a pattern layer that basically creates the interference patterns that allows the movement to be detected. So it creates the I guess the lines of the diffraction grating creates an interferometric pattern that then we detect, and our ASIC carries out some very clever signal processing to convert that unit of measure of the membrane into a very high quality audio signal.
So a diffraction grating of that scale must have incredibly small slits.
Yeah.
Incredibly small, yes. And that becomes a limitation of our package size as well, to be honest with you. I mean, right now our height of our package is 2.5 millimeters. We're not as in low. I think many MEMS out there might be 1.1, 1.15. So we do have right now a physical limitation as to the stack up, and that's largely because of the optical module.
Okay.
So it sounds like it's right down at the level of quantum electrodynamics type of a deal, where it's a two-slit experiment, and you can never quite be sure which slit the photon passes through. Yeah.
And then I think, yeah, so this is just to give you an insight on our manufacturability. So we have the Sensibel core, which is the MEMS design, the optics, the ASIC, and the package. And actually, here is a good drawing of the optics where you can see the MEMS is shown on the bottom here. This layer here is the diffraction grating, and this is the combination of the laser and photodetector. So basically, you have the light hitting the membrane and coming back. And they're all things that Sensibel have developed and they own. And then we have industry leading scaling partner in AAC, which take the optical module and the subcomponents of the ASIC and the MEMS, and they assemble it and carry out test. So we've taken this optical technology and streamlined it into the existing type of assembly and test that you would see for another MEMS microphone. So this is really enabling our ability to scale and to make these things efficiently and get them out to customers. And then on the sales side, this would be a combination of Sensibel and distributors and regional representatives.
Yeah,
But
right
go ahead.
now we have a small team. Mike is our well, besides the engineering team, Mike runs our applications engineering directly. He's the guy to go to technically for all of our customers, but we have a inside sales team, a marketing team. Everything is supported direct out of Oslo now. We're shipping everything. All the material will typically come into Oslo, and we ship directly from there. But yeah, we're small and nimble and getting extremely busy these days.
Okay, and is there any like black boxing of components? I mean, AAC is a bit of a monster, so is like some special sauce that you guys are manufacturing with like local partners in Scandinavia to kind of insulate yourself from AAC?
No, go ahead, Mike. I'll let you talk.
I think the biggest thing for me when I look at this, and I find it fascinating because I came from a capacitive MEMS microphone background. So I'd worked at TDK and I'd worked at Vesperon piezo MEMS, and really the ASIC does some very clever things and very sophisticated things. So when you do that inside an ASIC, it's well protected and it's something you just ship as an ASIC with a bonding diagram. And we have a calibration routine and everything that's pretty standard. But I think that type of a situation is good for controlling your own secret sauce and things like that.
Okay.
So that implies
Yeah.
then that there's inherently some significant nonlinearities in the system, but they're well known, so can be compensated by the ASIC.
Yeah, and there's some clever, I guess, transduction of signals. Yeah, I guess that covers kind of, you get into nonlinearities and things like that. But I think there's a few other things that the years of research at Syntef and the guys did, because other people have attempted to make optical microphones and not succeeded. And I think the years of research the guys put in really enabled, getting both the SNR and the overload point together, which is really makes it viable as a commercial product.
Yep. Yep.
And let me add, just because the optics, the stack of the optics, how everything's converted, we are natively digital. We have a few people come and say, well, can you do analog? You have an analog one? And we're like, well, then you have to convert all this really, really nice 80 dB low noise signaling through a D to A and potentially ruin it. So we're natively digital PDM, I2S, and TDM. That's actually programmed. Part of the factory programming is how do we, it's all more or less pretty much the same device, and in the factory it's programmed PDM, TDM, I2S. And so, and then there's some, adjustments because it does have an I2C interface. So there are some things that the customers can control internally, maybe some gain, maybe the low frequency roll off, maybe we have some filtering internal to it. So all of this is kind of customizable by the customer.
Okay.
You just mentioned low frequency roll off, and I noticed in the data sheet or the product brief, 10 dB minus 3 dB, 10 hertz to minus 3 dB. That's pretty low too. That's an interesting one.
Right. Yeah. Yeah. We see customers like that because if they're doing things that maybe active noise cancellation and things like that, they can really get all the low frequency energy and subtract it out. And then they have the capability of increasing it on the 10 hertz is pretty much what the MEMS kind of acoustic low frequency roll off is. And then on the ASIC, there's a high pass filter that they can adjust upwards if they prefer a higher cutoff point.
Mm. And so is that inherently the ability to get to pretty low frequency roll-offs is also closely related to the fact that you don't have a back plate then?
Yes, yeah. The ability to I think it's challenging in the capacitive world to do very low frequency roll off because you can get kind of a one-way pressure or a kind of a DC transient that could if you don't have good vent noise or sorry, if you don't have a good vent between the front and the back volumes, it could take a long time for the pressure to equalize for them, and the plates could be very stuck together. It could get stuck together, or there could be a discharge, or even if there isn't a discharge from one plate to the other, it can be just a lot of signal for the ASIC to handle because it's a voltage that it's outputting. We're picking up a light measurement, so we're not sensitive to excessive voltage, and we don't have a backplate, so there's it can't stick to it. So that's a degree of freedom that we've exploited because of our optical technology.
So the photodetector doesn't generate an analog voltage?
It does, but I guess it's not a direct injection of voltage onto the ASIC compared to a capacitive microphone.
Don't know if
Whereas a
just
capacitive microphone, you have a change in voltage that directly goes onto the.
Uh-oh. Where is everybody? Did I just lose everybody? I think we had a little blackout there for a sec. Can you guys hear me?
Roll off is just depends on the vent holes we put in the membrane. So we can increase it and we can just add more vent holes. Yeah.
Just interrupt for a sec. We had a little cutoff here on the recording about a minute ago.
Yeah, it's been kind of cutting. I've noticed it's been kind of cutting in and out. Everyone's moving a little bit. Everyone but me seems. Everyone, I feel fine.
What was that last question, Simon? Do you want to just recap that? And I could
about the 10 hertz in relationship to the backplate.
Yes.
I don't know if we
Yeah,
covered
so we're able to do 10 hertz low frequency roll off in part due to the fact that we don't have a backplate. If for a capacitive MEMS microphone, if you have a very low frequency roll off, they become susceptible to kind of DC pressure pulse changes that could push the diaphragm into the backplate, and it could be difficult to recover from. If we get a large excursion of the diaphragm, it can travel further and it can recover from it pretty easily.
The next one that cut off for me that I was interested in answer is the photo detector. What you actually measure off a photo detector is a voltage,
Yeah, so I guess our photo detector works. It does send an electrical signal from the optical module to the ASIC, but it's different to, a capacitive MEMS microphone changes a voltage that goes to a very high impedance input on the ASIC. For us, the photo detector sends an electrical signal that's a unit of measure of displacement rather than a direct voltage. So it's not as sensitive to these overloads, and it's a more controlled transduction method. So we can have an instantaneous recovery for even if you somehow manage to exceed like our acoustic overload point of 146 dB SPL. As soon as that stimulus goes away, we recover right away, and you get 100% normal operation if it after the stimulus goes away.
Okay, and then the next question was about the high frequency resonance. So all the MEMS mics I'm familiar with, they're usually about 20K, 24K type of a range.
Yeah,
quite a huge resonance.
So we're in the 20 kilohertz range. So it gives a flat response up to close to 20 kilohertz, and that suits our customers, and it's probably something we will adjust a bit on future generations depending on customer demand. We're not too constrained there.
Yep. So that leads into the next thing which you already just answered, is that the underlying response is again this below fundamental resonance, flat as a pancake until you start to have leakage, basically, I guess.
That's right. That's exactly it.
Around the diaphragm.
Yeah. So we have just a few little vent holes in the membrane that create that high pass filter and the low frequency roll off of 10 hertz.
Yeah.
Okay. Yep.
Is this our slide?
Yeah. No. Sorry.
I'll keep going then. And then, because I was having a look at that data sheet too, you're talking about 24-bit, 192 kilohertz sampling rate. That's becomes significant because it's sort of necessary if you want to have this dynamic range. Is 24 bits sufficient for 130 dB dynamic range?
Yes.
Is that actually, I don't know the calculation, but that must be pretty close to all zeros to all ones.
That's right. Yeah. So you have about 144 dB dynamic range from 24-bit.
Theoretical ideal.
And we have 132 bits inside that. So but one thing to I guess we like to remind our customers of is to maintain 24 bits in the signal chain, because if you have 16 bits, you start to create a bottleneck. But your bit depth will support that dynamic range, and then the sample rate is down to customer preference. Some customers use 48 kilohertz, and that's sufficient for a lot of audio applications. It'll give you your 20 kilohertz bandwidth. And then we've had others who are doing interesting things, maybe in the ultrasonic space, and they go up to 96 or 192 kilohertz. And they can, I think we're the only microphone that does 192 kilohertz sample rate, and there aren't that many that do, above 48 kilohertz. So we're unique with our 96 kilohertz sample rate too.
I think I saw somewhere where it mentioned I2S for ease of compatibility and so on, but PDM for lower latency. Is there some difference in latency between the two? I don't know about that. I'm curious.
Yeah, it's PDM is the lowest latency signal because you have one less stage of digital filtering, because it's a single bit signal. So there are customers that want a PDM microphone because all their processing is latency optimized, and they prefer to do that final stage, or they can do processing in the PDM domain itself, and have that type of control.
So
So
I'd say, so if you get PDM out from it, don't you just have to give that latency back by processing it on your receiver end? But you're just saying you could do PDM processing directly.
yeah, that's and I'm not a system expert in that really, but that's what the feedback we get from customers, that they're happy to do their own all PDM processing and be latency optimized.
Yeah, and what I've noticed too is, I mean, competitively, I think a lot of our competitors have focused on PDM. I think there's probably more devices on the market that are PDM, and so a lot of testing is done with our PDM mics just for basis of comparison, maybe putting into an existing system so they can truly see what 80 dB in their current system really buys them, and then at that point, then it's just an optimization. Is PDM most optimal for their system, or is it not? But we give them the opportunity with the same exact microphone to switch to I2S right away.
Okay.
Yeah, and we might sometimes have customers that are actually coming from an analog, like an ECM that's in the high 70s of SNR, and using an analog to digital converter with an I2S or a TDM output. So our microphone replaces two components in their signal chain. So it's a very efficient solution that way for I2S, and I think customers like that aren't latency critical. They might be doing an application where they're doing other filtering downstream that adds latency anyhow.
Okay.
Slightly different tech thing, because I'm curious about and the what kind of applications, and okay, we talked about ANC and sort of consumer applications, but how about studio recording and measurement microphones? Is that not pretty much?
But
Is,
you're now, Simon, you're stealing our thunder, I think, from another two slides. So we'll talk
okay.
about it. We have a slide that just talks about applications where we're being successful now. We'll talk to that real quick.
Okay.
Yeah. And I guess just to talk about the development kits, so we have the Aurora development kit that's built around our I2S and PDM microphones. So it's a plug and play USB audio solution for Windows, Mac, Android, Linux, and you have a switch on the board where
Raspberry Pi as well.
Raspberry Pi, yeah. And you have a switch on the board where you can switch from PDM to I2S, depending on which microphones you're evaluating. And then we mentioned about our microphone configurability and over the I2C interface. And we have, a switch on board where you can carry out some canned I2C writes. We provided pre-programmed to apply user gain on the microphone. So it's just more convenient if they're doing some field recordings and things like that. But it's really a plug and play solution, so that a customer unboxes it and 5 or 10 minutes later they're recording 24-bit audio and seeing the real living optical MEMS microphone doing its thing.
Mm-hmm.
Programmable user gate, what kind of resolution is that capable of?
So it's 24-bit. This kit goes up to about 96 kilohertz, and that's actually a limitation of the PDM decimation. Our I2S microphone, we can have go up to 192 kilohertz. So
Sorry, I actually meant for the I2C controls user configurable gain.
yeah.
What gain steps is it? Is it like a +3, +6 type of a thing?
That's right. Yeah, 3 dB steps. Yeah. Yeah. So they can they can change the sensitivity if they prefer, our default sensitivity is -46 to support the very high overload point. But they might, if they're doing a back-to-back comparison with another microphone, they might prefer to bring it up to like -36 or something like that.
Okay.
And then we have, so this is for our I2S and PDM microphone. And then for our TDM microphone, it's the time division multiplexing. So you can have up to 8 microphones on a single data line. So this is a very effective way of scaling up microphones for a microphone array. So we have, a circular array board with 8 microphones on flex. And the kit features are very similar to our other kit. It's compatible with Windows, Mac, Android, Raspberry Pi, and Linux devices. It's plug and play. And we, I guess, with the TDM interface, there are some configuration pins on the microphone that tells it should the microphone be at like time slot 1, 2, or up to 8. So we configure that in the board. So you can see here, mic 1, it'll show up in the mic 1 time slot. So we do all that for the customer. So really for somebody who's doing beamforming, this is a beamforming ready solution. They can concentrate in the software. We have the 8 microphones configured on TDM. The USB brings 8 channels of audio into your computer. So they can just start recording and start testing out their algorithms. And it supports 24-bit audio and 44.1 or 48 kilohertz sampling rate. One thing to note with the with TDM, you're running things very fast to fit 8 microphones into the single data line. So there's no kind of free lunch with that. You can't do the 192 kilohertz. You're just limited to 48 kilohertz. But for most applications, that's plenty for our customers.
Okay.
So yeah, that's our Polaris development kit. We're getting a lot of interest on this. Actually, a lot of people see the value in being able to make an array like this and just get up and running very quickly.
So the gain and phase matching of the devices themselves is pretty good then.
Yeah, so our microphones are ±1 dB sensitivity, and that's the spec. They run very close to each other, much tighter than that. And their phase matching is very tight also, especially with that 10 hertz low frequency roll off. That gives you very tight phase matching. If your low frequency roll off is down around 10 hertz, then it means the matching at like 100 hertz or 250 hertz starts to get very tight. So yeah, it's for beamforming and any processing that's dependent on phase matching, it's very valuable.
And I'm going to give Mike a little shout out because he's the one that created both of these boards himself, the Polaris and the Aurora. And so, yeah, definitely need to give Mike thank you. It's a great, very well done and very well received by customers these days.
Okay.
So we're about getting the end. So talking about where we're playing right now with customers, where we're being successful. So certainly measurement microphones, reference microphones, everything where low noise is important. Environmental monitoring. Surprisingly, again, the beam forming with the Polaris boards, we're having a hard time keeping those in stock. Everyone's purchasing a Polaris board with 8 TDM mics, and so lots lots of threat detection, drone detection, gunshot detection. It just, anywhere from systems with 8 to 16 and 92 to 200 microphones is not uncommon, for stuff that we're involved with now. Certainly conferencing systems, the very low noise, putting these microphones up in ceiling tiles per se, and being able to pick up noise, sound across the room. All of these are very viable programs and projects for us. Where we're seeing, we're still working with customers, and actually, a lot of the customers that we're dealing with and luxury products, higher end luxury type consumer products are really starting to do testing on ANC. So the biggest thing for us, even at we talk about next CES, how do we showcase 80 dB SNR? What can we do to showcase it other than putting on headphones and trying to hear the difference and not hear the hiss and everything else? So our challenge now is working with customers, and again, all part of the brand awareness is working with the right customers and getting things out that we can show that really showcase 80 dB SNR. Now the professional audio recording, absolutely, we're working with the companies for to look at the Neumann mics and the Sennheisers, all these different variation, very low noise studio quality microphones, and we have those engagements now. But ultimately, as the problem statement that Mike showed with the cell phones in the beginning, I mean, I was involved with Knowles back in the early 2000s. The big part of this and why we're not actively involved with the cell phone guys is, again, ramping capacity. Our next generation product is truly going to be the scalable version of our product. And as I was saying, I was with Knowles in the early 2000s. And the MEMS microphone, the first MEMS microphone, was just becoming popular at that time. And I remember I was part of the Motorola team, and
hold on a sec.
500,000 units. And they were the first. That was the first Motorola program to adopt the MEMS microphone. And lo and behold, it turned to be 20 million units plus per year. So you have to be ready for that kind of explosion, and that's what we're working towards.
Okay, good stuff.
I'm going to go in with one more technical point. As just how about power consumption?
Yeah, so we're, I guess, at our same performance point as other MEMS microphones. We consume about the same power. As you want to get more performance, you have to consume a bit more. So we're in the single digit milliamp range at our very highest performance. And then we can, if somebody wants to, say, have 70 dB SNR, it's less than a milliamp. So we're on the same kind of performance to power kind of ratio as other MEMS microphones. The difference is, I guess, is they throw more power at the device. They hit a ceiling for performance, whereas we keep on going.
Okay.
About a milliamp then.
Yeah. I think that's what Michael said. All right. Okay, so that's a pretty comprehensive introduction, and I think everybody can take it from here. We'll put the contact information for Sensibel, their website, etc., below, and people can check it out. We encourage people to do that and like, subscribe, all that good stuff. So, Mike and Tom, thanks for joining us today.
Absolutely. Very much. Yeah. Thank you. Thank you for the invite.
Thank you for having us.
Yeah, appreciate that. Simon, very nice to meet you.
Good to meet you.
All right. So we'll see you guys on the next episode, everybody. Thank you. Bye-bye.
Thank you, everybody.
Okay, thank you. Bye.
Bye-bye.